Hi guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So in our discussion today, we're going to look at another aspect of the relationship between the potential difference and the current through a circuit. And this is going to assist us to develop some of the laws which we are going to be applying in our various other sets of perhaps problem sets or some of the evaluations we are going to come across. And we're going to look at the concept of Ohm's law. And of course, Ohm's law was developed by George Ohm, which he came across due to various measurements he had done of a resistance of metal wires. And of course, he discovered a particular relationship between the potential difference and the currents. And this, of course, gave him one of the ways in which you could illustrate this specific aspect of this particular relationship. Now, in this case, he announced his famous Ohm's law, and we're going to look at a particular relationship which is going to be dealing specifically with some of the conductors. In this case, which I've mentioned, like of course, metal wires, which or some of the wires which he had used, which were basically conductors. Now, in physical conditions, we are going to see that, of course, the flow of currents through a conductor is going to be given in a particular set of a relationship which I have described. And this is going to have some kind of a proportionality with what we refer to as the potential difference. Now, in this case, Ohm found out that, of course, if the conditions are unchanged, the current flowing through a conductor is directly proportional to the potential difference across that conductor. So in this case, therefore, he came up with the relationship of the potential difference and the currents using this specific equation which I'm going to give. So he found out that the potential difference across a conductor is directly proportional to the current that is flowing through it. And this relationship, of course, is going to be given as, of course, relationship 1. Now, in this case, we can introduce a constant for this relationship whereby we are going to have V is equivalent to Ri, whereby our R is going to be defined as resistance. Now, in this case, this is going to be a relationship that is going to be realized from these specific measurements that were made by George Ohm. And the resistance in this particular case we're going to see is basically a quantity that is going to depend on the nature of the materials and, of course, its dimensions. And in this case, mentioning the dimension, then therefore I'm going to particularly be emphasizing on the concept of cross-sectional or the area of these specific materials. Now, in this case, we are going to have a mathematical relationship, as I've said, which is going to be the ratio between the potential difference and the current that is going to flow through it. And this can be given in terms of V over A in some other relationships which we are going to come across. And the SI units or the SI units used for this specific relationship is going to be defined in terms of ohms. So basically, this has been named after George Ohm, who had done this specific experiment. Now we're going to use this one in terms of perhaps a notation which is going to be given in terms of this specific illustration for omega. So in case we come across them, then we're going to be notifying that this is an SI unit that is going to be defining this relationship of omega. So therefore, we're going to look at this specific aspect of resistance. And as we can see from a literal point of view, is going to be the ability to oppose a specific aspect of perhaps motion. And there are some causes which are going to be associated with this specific aspect of resistance. Now, in this case, if we are going to look at the potential difference which is going to cause a flow of current, then therefore this aspect of resistance is going to be an aspect which is going to oppose this specific aspect of a flow of charges through a conductor. Now, the implication of this is that the resistance of a conductor is going to physically imply that there's going to be a position of a flow of charges, as I've said. And as I mentioned, of course, for metals, which we are given in one of our illustrations, we are going to see that metals are going to be consisting of electrons in their basic structure. And we're going to see that basically the flow of electrons are going to be indicating the flow of negative charges. But as we had said, of course, we're going to see that we can have the direction of flow of current being given using this specific indication. And of course, this has been conventionally been used for indicating the direction of flow of the positive charges using that specific notation. So in this case, in either way, we are going to see that there's going to be a flow of charges for the positive and negative. Now, in this case, if the resistance is the ability to oppose that flow of charges, then therefore we can be able to quantify that specific relationship using this specific aspect, whereby we are going to give resistance in terms of V over I given as such. Now, this particular phenomena occurs due to collision of these specific moving charges with other ions and atoms. And of course, this motion is going to be opposite, and therefore it's going to define a resistance of that specific material. Now, as we are going to see later, different materials are going to display various aspects of their resistance. And this, of course, can be measured using this specific relationship which I've given in that particular case. Now, in my definition, there's an aspect which given, of course, of this specific resistance of materials, whereby they said that it's going to depend on the material and its dimensions. Now, in this particular case, we're going to consider the aspect of length, which is going to form one of our dimensions, which are physical aspects which can be measured in this particular case. So we're going to therefore consider length and perhaps area, which I've mentioned for specific types of conductors, as we're going to come across. So there's a difference between this one given in terms of amperes and area. So this one is specifically mentioned for area, which is an aspect that is going to be affecting this aspect of resistance. Now, in this case, the resistance is directly proportional to length and inversely proportional to the cross-section area. And therefore, from this one, we can develop a relationship whereby resistance is directly proportional to length, but inversely proportional to the cross-section area. So perhaps I can give this one in terms of a cross-section area given as such. So this is going to give us another relationship from the first one, which we had given as 1. We're going to see that taking account of the dimensions which we have mentioned, therefore resistance is going to be directly proportional to the length of that specific conductor, and the cross-sectional area inversely proportional to the cross-section of that specific conductor. Now, combining this specific relationship, just as we have done for the first one, therefore we can come up with a relationship that is going to assist us find the relationship between length, area, and resistance, whereby we're going to have this one given in terms of resistance is equivalent to, so I'm going to use this rho at this particular point, length over area given as such. So in this case, the rho is going to indicate resistivity of a material. And later on, we're going to see that different materials are going to display this specific aspect of resistivity, which is going to be particular. And in that case, then therefore, we're going to have this particular resistivity as a constant value for materials, or given materials, which is independent of size and shape of the various conductors. Now, this is going to be given a specific type of dimensional measurements, which are going to be given in terms of ohm meter, which is going to be a unit of measurement. So this is going to be given in terms of ohm meter given as such, and this is going to be used in measuring resistivity of materials as we come across them in our various discussions. Now, in this particular case, I'll be giving a particular example on the concept of this Ohm's law. But in summary form, I've said that basically Ohm's law is going to be dealing with the relationship between the ratio of the potential difference and the current, and the current potential difference and current. And the potential difference and current is going to give us what we refer to as resistance, which is going to be opposition to the flow of our charges through a conductor. Now, as we have said, of course, this is going to depend on length and cross-sectional area of that specific conductor. And that's going to give us in a summary way the relationship between resistance and these other forms of course, current, the potential difference, length, and a cross-sectional area. So in this case, catch us in our next videos. We're going to look at one of the evaluations of this specific aspect of our resistance, and it's going to assist us appreciate Ohm's law as we come across it in our various discussions. So that is it for now, guys. Bye, God bless you. Catch us in our next video.